Everyone knows that solid H2O floats in liquid H2O. That is, that ice floats in water. And there doesn't seem to be anything surprising about this. The solid is evidently not so dense as the liquid. And in fact, this behavior of paraffin is characteristic of most substances. Generally speaking, a given substance is denser that makes it behave in this unusual fashion. First, to give us a basis for comparison, consider a more typical substance, benzene. We have some benzene, which is in the process of melting. Go 8. The benzene is remaining at 5.5 degrees, which is close to its melting point. As the benzene absorbs heat and melts, it expands, forcing some liquid up this narrow tube. The benzene continues to melt as it absorbs heat. Now the benzene is all liquid, and it is still absorbing heat. The temperature has begun to rise above the melting point. As the liquid benzene becomes warmer, liquid benzene becomes, the greater the volume it occupies, or in other words, the less dense it becomes. So benzene expands when it is warmed and changes from a solid to a liquid, and it continues to expand as it is warmed in the liquid state. This time, we're starting with the drop of benzene in the liquid state. The mercury in the dish is simply the base of a column of mercury going up to the drop of benzene. The mercury will register any changes in the benzene's volume. In order to raise the temperature of the drop of liquid benzene, hot water is being circulated around it. The drop of benzene is very small. That's why we cannot see that it is expanding. But watch the drop of benzene carefully. The hot water is continuing to raise its temperature. As the benzene reaches its boiling point, it vaporizes. That is, it changes from the liquid to the gaseous state. There is a tremendous expansion, indicated by the fact that the top of the mercury column is pushed downwards. The hot water is still raising the temperature of the benzene, and the benzene continues expanding in its gaseous state. So it seems that at any point, an increase in temperature causes benzene to expand. Now let's follow the same procedure with H2O. The H2O in this flask is melting, going from solid ice to liquid water. Just as with the benzene, we can see the temperature on the thermometer and the volume by the level in the narrow tube. As long as the H2O is melting, its temperature remains at its melting point, 0 degrees centigrade. But notice that as the H2O is getting warmer, it is contracting. Its volume is decreasing. This is the opposite of what happened to the benzene. The H2O is still absorbing heat. The last particles of ice melt into liquid water. Now the temperature begins to climb above 0 degrees centigrade. As the water is heated above 0 degrees, it continues contracting. The H2O, entirely liquid, is still absorbing heat. The temperature of the water has risen to 4 degrees centigrade. And now the level of the column of water in the tube seems stationary. Even though the water is still absorbing heat and its temperature is rising, it is no longer contracting. The temperature is now approximately 4.5 degrees centigrade. The water column in this tube is reversing its direction. It is now going up instead of down. As the water is warmed above 4 degrees, it expands. The temperature of the water is up to 10 degrees, and it is continuing to expand or increase in volume. Now we shall start with a drop of liquid, just as we did with the benzene, but this time it is water. Again, the mercury will register changes in volume. A hot bath is used to raise the temperature of the water. The water reaches its boiling point and expands as it's vaporized into gaseous steam. And as we continue heating the steam expands. In general, H2O at a temperature of 4 degrees or above increases in volume with any increase in heat. Now let's consider this same data, but in reverse. A given quantity of benzene will contract as it's cooled. As heat is taken from it, it decreases in volume, passing from the gaseous to the liquid to the solid state. This is true not only of benzene, but of most substances. The less heat, the less molecular motion, and the less volume. H2O in gaseous form, that is steam, also decreases in volume as it is cooled. It continues contracting as it condenses into water and as it's cooled in its liquid state. But when cooling water reaches 4 degrees centigrade, it begins to expand, and it continues expanding as it freezes into ice. It is not difficult to demonstrate the great force of this expansion of H2O as it goes below 4 degrees. We are filling this cast iron container with water. And now we screw the handle tightly into position. We place the cast iron container in a beaker filled with dry ice and acetone. This mixture of dry ice and acetone has a temperature of about -80, well below the freezing point of water, and should therefore freeze the water inside the cast iron container into ice quickly. The expansion of the H2O, as it was cooled below 4 degrees centigrade, created so much pressure that it exploded the cast iron container. Most other substances contract when freezing. How can we account for this unusual behavior of water? Well, we know that it takes energy to separate the hydrogen and oxygen from water. We usually use electric energy. This is because the hydrogen and oxygen are held together by bonds. Here is a highly simplified representation. The electrons of the 2 hydrogen atoms are shared with the oxygen atom in a molecule of H2O. But because the oxygen nucleus has a greater positive charge than the hydrogen nucleus, the shared electrons are more closely associated with the oxygen nucleus than they are with the hydrogen nucleus. This electron arrangement makes the water molecule relatively negative at the oxygen end and relatively positive at the hydrogen end. It's been determined that the hydrogen atoms attached to the oxygen atom are at an angle of about 105 degrees. This bent shape increases the polarity of the H2O molecule. Thus, it's possible for a number of H2O molecules to bond to each other, positive ends to negative ends. In steam or hot water, the H2O molecules are relatively far apart, and there is relatively little bonding. As water is cooled down to 4 degrees, the molecules come close enough together for many of these bonds to form. As you can see, when the molecules are all bonded together, they take up more space. The bonding of H2O molecules is called hydrogen bonding because it occurs at the hydrogen end of the molecule. Water expands when cooled below 4 degrees because the water molecules join to form a loose open network, which is why ice is less dense than water and floats on water. Even well above 4 degrees, there is enough hydrogen bonding in water to cause the molecules to cohere or stick together strongly. A drop of water holds its spherical shape. But a drop of benzene, in which there is practically no bonding between molecules, spreads out. The same hydrogen bonding is responsible for what is generally called the surface tension of water. It's quite easy to float a razor blade on water because of the linking of H2O molecules to each other. But benzene, in which the molecules are not bonded together, will not support a razor blade. Much of the familiar behavior of water, such as its cohesion and surface tension, and its expansion when it freezes, is a result of hydrogen bonding.